Well, you see, there's a quiet question that seems to linger in the air. One that follows us from the moment we wake to the moment we drift into sleep. Why does everything slowly fall apart? Why does a warm cup of tea grow cold? Why does a tidy room surrender to clutter? And why do our memories feel like soft footprints fading on a shoreline? Perhaps, and this is the curious thing, these everyday moments are whispering the same story the cosmos has been telling since the very beginning. A story about entropy. And you know, when you start to listen closely, you realize entropy isn't just a scientific idea tucked away in textbooks. It's a companion, shaping the flow of time, sculpting the rise and fall of stars, guiding the way matter arranges itself into planets, people, and passing thoughts. I suppose the real wonder lies in noticing that entropy is not merely chaos, but possibility. It's the measure of how many ways the universe can be itself, and suddenly, well, the world feels different. You begin to wonder, if entropy is the arrow of time, then what does it mean for us, tiny travelers moving through this vast and ever-unfolding landscape? How does understanding disorder help us see our own lives more clearly, more gently, here in the quiet hours of the night? Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. Well, you see, when we begin to talk about entropy, it helps to imagine ourselves standing at the edge of something both familiar and endlessly mysterious. Perhaps you are in your room right now, the soft light pooling on the floor, a few objects resting just slightly out of place. And that is the thing. Even in a quiet room, entropy is already at work. It is not loud. It is not dramatic. It does not arrive with a crash. Instead, it creeps in gently, the way dust settles on a forgotten shelf, or how the warmth of your hands slowly drifts away into the cool night air. Entropy, in its simplest spirit, measures the number of ways things can be arranged, the number of microscopic stories hiding behind what we see. You know, we often say entropy is disorder, but perhaps that word misleads us. Disorder feels like a judgment, as if the universe should be ashamed of its natural tendency to explore possibilities. But entropy is not moral. It is not messy in the way we think of mess. It is simply a count of arrangements, of pathways, of hidden configurations beneath the surface. Take a tidy room, for example. Everything placed neatly, books aligned, blankets folded. There are only a few ways the room can look tidy, which means the entropy is low. But give it a few days, a few moments of movement, a few hurried mornings, and the objects begin to drift. Suddenly there are millions of tiny variations, millions of ways the room can appear slightly different. That, you see, is higher entropy. Not because the room became worse, but because it became statistically more probable. And that is one of the profound truths tucked inside this idea. Entropy is tied to probability, to what is likely in a world driven by the ceaseless dance of microscopic particles. Perhaps imagine a box filled with gas. From far away it looks completely still, but inside, every molecule is darting, colliding, bouncing in every direction with staggering speed. On the microscopic level, there are countless configurations those particles can take. Some of those arrangements are rare and orderly, like all the gas clustered in one corner, but that is so improbable that you could wait longer than the age of the universe and still never see it happen spontaneously. More likely, overwhelmingly likely, is the state where the gas spreads evenly through the box. And so entropy gently guides us toward the common, the probable, the natural unfolding of possibilities. This connection between entropy and probability feels almost poetic if you tilt your head just right. It suggests that the universe is not trying to fall apart, but rather trying to explore every arrangement available to it. And the more arrangements possible, the higher the entropy. You know, even something that seems perfectly still like a rock resting in the early dawn, is humming with microscopic motion. Atoms vibrate, electrons swirl, energy shifts in imperceptible currents. Stillness, in many ways, is only a trick of the eye. Beneath the calm surface lies a restless sea, and entropy helps us make sense of that hidden restlessness. I suppose what makes entropy so intriguing is this double view it offers. On one side, the macroscopic world of objects we can touch, cups of coffee growing cold, ice melting in our hands, ink spreading across water. On the other side, the microscopic world of particles and probabilities. Entropy is the thread stitching these layers together. It tells us that the warmth in the coffee is just the rapid jostling of molecules, and as they slow and spread their energy outward, the number of ways those molecules can arrange themselves increases. The coffee cools, entropy rises, time moves on. Well, that brings us to something strangely comforting. Entropy does not measure disorder in the emotional sense. It measures how surprised we should be by a state. A high entropy state is one we expect, like a shuffled deck of cards. A low entropy state is special, like pulling out a perfectly ordered deck. And because high entropy states outnumber low entropy states by unimaginable margins, that is where systems naturally drift. Not because they want to, but because probability nudges them there. And that gentle nudge is everywhere, even in our breath. When you exhale, the molecules of air leaving your lungs disperse into the atmosphere, spreading wider and wider until the pattern of your breathing becomes part of the great atmospheric mosaic. Entropy lifts your breath into the world and lets it vanish among countless others. It is a reminder, perhaps, that everything we do becomes part of a larger tapestry, a tapestry woven not by intention, but by the simple mathematics of possibility. I suppose if we step back for a moment, we might ask, what does it mean that entropy tends to increase? Does it mean the universe prefers chaos? Not exactly. It means the universe prefers the likely. High entropy states are like vast open landscapes, while low entropy states are narrow, delicate peaks. And it is far easier to wander into a wide plain than to remain balanced on a thin ridge. Imagine a jigsaw puzzle fully assembled. There is only one way the pieces fit perfectly. But scatter the pieces across the table and suddenly, there are countless ways they can lie, overlapping or separated, flipped or turned. The scattered state has higher entropy because there are far more possible configurations. The assembled picture is beautiful, yes, but fragile. And perhaps there is something humbling in that. It tells us that order, harmony, structure are rare moments in a universe full of wandering possibilities. And yet, we cherish those rare moments. We create them. We live inside them. Our bodies, our memories, our civilizations all depend on holding pockets of low entropy against the great cosmic drift. And this is where the concept becomes strangely intimate. Because when we try to understand entropy, we aren't only learning about physics, we're learning about why the world feels the way it does, why the morning becomes afternoon, why youth becomes age, why heat slips away, why patterns blur, why structures loosen. Entropy is woven into every experience of time. And even here in 2025, as we explore deeper theories and newer technologies, the fundamental nature of entropy remains steady, timeless, quietly shaping our reality. Yet, for all its inevitability, entropy is not something to fear. It is not a villain lurking in the dark. If anything, it is a patient storyteller. It explains why certain events unfold and others do not. Why you never see shattered glass leap back into a perfect cup. Why scents drift outward but never concentrate themselves again. Why a tidy room demands effort, while a messy one grows effortlessly. Entropy reminds us that the default direction of the world is outward, expanding into possibility. And our role, in a way, is to create islands of order, where we choose to carve meaning out of the vast statistical landscape. Perhaps that's one of the beautiful paradoxes of being human. We live in a universe that leans toward spreading out, and yet we gather things together. We build, we arrange, we remember, we tell stories. Each act of creation is a small defiance of entropy, a momentary holding of structure in a world that prefers to drift. And yet, without entropy, none of this would move at all. There would be no change, no flow of energy, no unfolding of time. Everything would simply sit, frozen in perfect symmetry, forever. So entropy, well, it is the very thing that makes motion possible. It is the quiet engine beneath existence. And you know, once you begin to see the world through this lens, even ordinary scenes take on a new and shimmering clarity. A melting ice cube becomes a lesson in probability. A crowded city hums with the constant exchange of energy and information. A gust of wind scattering leaves across the ground becomes a choreography of countless microstates. Entropy becomes the language of change. So as we linger here, gently holding the idea of entropy in our hands, feeling its weight and its wonder, we might ask ourselves a final question before moving on. If entropy tells us what is likely and which direction time prefers, then what deeper stories emerge when we follow that arrow across the vast expanse of history, from ordered beginnings toward unfolding complexity? And that, well, leads us naturally into the next chapter, where the birth of entropy in human thought begins to shape the way we understand the universe itself. Well, you see, when we look back into the 19th century, it feels almost like leaning over the railing of a ship as it glides through a foggy dawn. Shapes begin to form. Ideas take their first breaths. And somewhere in that misty intersection of steam, metal, and human curiosity, the concept of entropy was born. It did not emerge from starlight or galaxies, not yet. Instead, it rose from engines, from clattering pistons, from the very practical question of how to turn heat into motion. That is the thing. Great cosmic truths often begin in places that feel terribly ordinary: a factory floor, a boiler room, a workshop filled with the scent of oil and iron. Entropy slipped quietly into human thought through the study of heat engines, those early marvels that carried the ambitions of an industrial age. Engineers noticed something unsettling. No matter how cleverly they designed their machines, no matter how polished the gears or how precise the valves, some energy always slipped away as useless warmth. It leaked into the air, the water, the metal itself. This loss seemed stubborn, inevitable, as if nature had drawn a boundary around what humans could accomplish. And that persistent loss demanded an explanation. Why could no engine reach perfect efficiency? Why did heat resist being fully transformed into work? These were not philosophical questions at first. They were practical frustrations. But as people wrestled with them, a deeper truth began to reveal itself. Enter Rudolf Clausius, a quiet mind with a talent for glimpsing the invisible. You know, he did something remarkable. He took this idea of lost energy and gave it a name that would echo across centuries: entropy. A word born from Greek, roots meaning transformation and turning inward. Clausius used the term to describe the part of energy that could no longer be harnessed to do useful work. He was trying to capture the essence of irreversibility, the way heat naturally spreads instead of concentrating, the way processes unfold in one direction and resist being unwound. At the time, it must have felt almost mystical, this attempt to bottle the flow of nature into a single concept. But perhaps, and this is where things get truly fascinating, Clausius was only laying the first stone of a path others would soon widen. At first, entropy was tied tightly to heat engines. It was a bookkeeping tool, a formula to remind engineers that some energy was always slipping beyond reach. Yet even then, there was a feeling that something larger was humming beneath the equations, some deep law of how the universe itself behaves. And if Clausius had the intuition, Ludwig Boltzmann had the courage to follow that intuition into the microscopic world. Boltzmann, well, he saw entropy not just as a quantity, but as a bridge between worlds. He imagined the frantic, chaotic motion of atoms and molecules, darting and colliding in an endless, invisible dance. And in that dance, he found the meaning of entropy. It was not simply lost energy. It was the number of possible microscopic arrangements that corresponded to what we see macroscopically. He tied entropy to probability in a way that felt almost poetic. A system with high entropy simply had more microscopic ways to be itself. A system with low entropy had fewer. Suddenly, disorder was not a judgment but a statistical truth. Boltzmann believed in this so deeply that the essence of his idea was engraved on his tombstone, a simple equation capturing one of the most profound insights into nature humanity has ever had. Perhaps there is something tender in that, the way a lifetime of struggle, debate, and vision can be reduced to a few carved symbols, resting quietly in stone. And his work was not immediately embraced. Many of his contemporaries resisted the microscopic interpretation of entropy. At the time, atoms were still hypothetical. Some physicists doubted their existence entirely. Boltzmann's ideas seemed speculative, almost reckless, as if he were trying to build a cathedral out of air. Entropy, in those early days, caused more than a few headaches. It was confusing, counterintuitive, slippery. People misunderstood it, debated it, rejected it, embraced it again. The concept seemed to resist simple explanation, and perhaps it still does. Yet even in its most contested moments, entropy carried a quiet power. It hinted that beneath the surface of things lay a deeper order, or perhaps a deeper freedom, governed not by purpose but by probability. And that suggestion, that whisper, would ripple far beyond the boilers and pistons that birthed it. As time passed, entropy grew larger. It slipped out of the factory and into the realms of pure physics. It became one of the pillars of thermodynamics, shaping the way scientists understood heat, work, and the flow of time itself. Clausius had opened the door, but Boltzmann walked through it with unwavering conviction. And once entropy rooted itself in thermodynamics, it began to stretch, to unfold, to touch fields of study Clausius could never have imagined. Chemistry, biology, information theory, cosmology. Entropy became a kind of universal grammar, a quiet rulebook for understanding why systems behave the way they do. And perhaps this is where the story turns from scientific history to something more human. Because every new theory, every new insight about entropy carries with it the echo of struggle. Clausius wrestling with equations, Boltzmann wrestling with skepticism, all of them wrestling with the stubborn fact that nature does not always bend to our intuitions. Entropy taught us humility. It told us that perfection, especially in the form of perfectly efficient machines, belongs to imagination, not reality. It reminded us that we are creatures living in a universe where certain losses are inevitable, where heat disperses, where order gives way to possibility. Yet I suppose the beauty of entropy lies in its reach. What began as a tool for understanding steam engines now helps us understand black holes, living cells, weather patterns, memory, computation, and even the heat death of the cosmos. Entropy has woven itself into every scientific narrative, from the smallest molecules to the largest galactic structures. Today, in 2025, its presence is so widespread that it feels almost like a quiet companion in every laboratory, every data center, every theory about the fate of the universe. Science students learn it early. Researchers invoke it constantly. Entire fields depend on it. And still, even now, entropy holds mysteries we haven't fully unraveled. It is strange, isn't it? How an idea that began with the frustration of engineers has become a guiding principle for understanding the universe. But that is the nature of scientific ideas. They grow, they evolve. They surprise even their creators. Entropy began as a question about waste heat, yet it has become a question about the nature of time, the unfolding of complexity, and the destiny of everything that exists. Perhaps part of its resonance comes from its duality. On one side, entropy describes something inevitable, the way systems drift toward states with more possible configurations. On the other side, it challenges us to look deeper, to ask why these probabilities exist in the first place, to wonder how order emerges, how patterns form despite the pull of entropy. It is both a constraint and an invitation, a limit and a lens. You know, when Clausius named entropy, he likely did not imagine it would one day help us interpret the temperature of black holes or explain why information cannot be destroyed without cost. Boltzmann could not have foreseen the full blossoming of statistical mechanics into quantum theory and cosmology. Yet their ideas planted seeds that would flourish long after their lifetimes, stretching into unexpected terrains. That is the quiet miracle of scientific thought. It outlives us. It continues to grow even when we can no longer tend it. And perhaps, if we listen closely, we can feel the gentle thread connecting those early engine rooms to the vastness of modern science. The hiss of steam giving way to the hum of supercomputers, the heat of furnaces giving way to the glow of distant galaxies. Entropy, ever patient, ever expanding, remains at the center of it all. It has become a universal story, whispered in equations, woven into experiments, guiding us through mysteries we are only beginning to fathom. Yet, for all its power and presence, entropy's early history reminds us that every great scientific truth begins with curiosity, confusion, and a few stubborn questions. Why does heat flow the way it does? Why can't machines be perfect? Why does the world refuse to run backward? These simple inquiries open the doorway to everything that followed. And as we gently close this chapter, lingering for a moment with Clausius and Boltzmann, with their equations and doubts and visions, another question begins to rise. If entropy emerged from the study of engines, and if it grew into a pillar of thermodynamics, then what exactly does thermodynamics tell us about the universe and the unbreakable direction of change? Well, that is where our journey naturally leads next, into the heart of the laws that bind heat, energy, and time into a single, flowing story. Well, you see, when we step into the realm of thermodynamics, it feels a bit like entering a grand old library whose shelves stretch beyond the horizon. The air there is warm, humming with the presence of countless processes unfolding quietly, inevitably. And at the very center of this library, inscribed in letters that seem almost carved into the architecture of reality itself, is the second law of thermodynamics. That law, is not loud or flamboyant. It doesn't shout. Instead, it whispers something steady and unyielding. In a closed system, entropy never decreases. It either rises or, in the rarest of balanced instants, remains still. Perhaps the beauty of this law lies in its simplicity. It tells us that there is a direction to things. A warm object cools. A hot drink loses its heat to the room. A block of melting ice does not reassemble itself into shimmering crystal unless we force it to, injecting energy like a sculptor trying to reverse the flow of time. And that's the thing. Thermodynamics is less about the microscopic details and more about the grand sweep of change. It does not care which molecule goes where or how many times they collide. It cares only about the larger pattern, the overall movement of energy, the path from what is ordered and improbable toward what is common, expansive, and statistically vast. Perhaps you've held a cup of hot tea on a cold evening. You feel the warmth radiating into your palms, a quiet comfort, but leave it alone for a few minutes, and the warmth seeps outward, dispersing into the room, its heat returning to the world. This simple scene, familiar and gentle, is a lesson in entropy. Heat flows from hot to cold because there are far more possible microscopic states in which the warmth is spread out than concentrated in one place. The second law is not a tyrant forcing heat to move. It is a storyteller explaining why the world prefers the likely, and the likely, more often than not, is the state of higher entropy. There's a sense of inevitability here, as if the universe is always leaning in one direction. The second law tells us that no engine, no matter how clever in design, can ever turn all the heat it receives into useful work. There is always some energy slipping through our fingers, dissolving into the environment as warmth that cannot be recaptured without spending more energy than we gain. Engineers and scientists have tried for centuries to imagine the perfect machine, one that runs indefinitely, producing work without waste. But nature, patient and firm, answers every attempt in the same soft voice. No. A perpetual motion machine of the second kind simply cannot exist. And perhaps this limitation is not a barrier, but a kind of cosmic truth. To produce work, to move things, to create change, you must also create entropy somewhere else. A steam engine chugging along the rails warms the air around it. A car engine leaves behind not only exhaust, but also heat radiating from the hood. Even your body, quietly breathing, thinking, moving, must release heat to maintain its astonishing interior order. The world at every scale seems to behave as if entropy is the cost of doing anything at all. What makes thermodynamics so mesmerizing, though, is the way it speaks in broad strokes. It doesn't need to know how every particle behaves. It relies instead on averages, flows, gradients. It cares about direction more than detail, and this means that the second law applies not only to engines and machines, but to stars, planets, oceans, and even the thoughts drifting through the human mind. Whenever energy is transformed, whenever work is done, entropy rises somewhere, like a quiet balancing of cosmic books. Take the simple example of a metal spoon placed in a bowl of hot soup. At first, the spoon is cool, the soup warm. But the moment they touch, the story begins. Heat flows from the soup into the spoon, racing along the metal, distributing itself until spoon and soup reach the same temperature. This final state, uniform and calm, has higher entropy than the initial one. And once it happens, well, you can't just wish the heat back into the soup. To reverse that flow would require external energy, a kind of magical intervention, because the natural path is always toward spreading, sharing, smoothing out. Perhaps the most poetic part of thermodynamics is how it shapes time. The second law doesn't merely describe energy flow, it explains the arrow of existence. A cold object warming spontaneously from its environment would be like watching a broken glass leap together on the floor. You could film such a thing, but you would never witness it in real life. Thermodynamics whispers that these reversals are technically possible, but so staggeringly improbable that the universe might as well forbid them. And this improbability is what gives rise to the feeling of time moving forward. Without entropy, time would lose its meaning, processes would become reversible. The universe would be like a river with no current, a story that can be read both directions without contradiction. But because entropy tends to increase, we experience childhood before adulthood, warmth before cooling, patterns before dissolution. The laws of motion don't tell us why time has one direction. Entropy does. Now imagine a closed system, something sealed off from the rest of the world. In such a place, entropy can only rise, never fall. It climbs like water filling a valley, or like mist creeping along a landscape soft and unstoppable. But real systems, of course, are rarely perfectly closed. We open doors, we heat and cool rooms, we move things around. And in doing so, we cheat entropy locally by increasing it globally. A refrigerator, for instance, can keep its interior cold and orderly, but the price is heat pumped into the surrounding kitchen. The kitchen's entropy rises more than the interior's entropy falls. The balance sheets of the universe remain intact. Thermodynamics, in this sense, teaches us a kind of humility. No matter how clever our devices become in 2025 or beyond, they cannot escape the quiet mathematics of entropy. A turbine in a power plant converts heat into electricity only with some loss. A data center hums with energy and sheds heat that must be carried away. Every act of computation, every spark of chemical reaction, every shift in a mechanical system leaves behind an echo of disorder in the world. Some might see this as a limitation, but perhaps it is more like a rhythm, a natural cadence of the universe, heat flowing from warm to cold, processes unwinding, energy dispersing. If entropy never increased, nothing would happen at all. No engines, no weather, no life. The second law creates the very conditions that allow stars to shine, winds to blow, and cells to respire. Entropy is not merely a measure of loss, it is the engine of change. Even the way machines behave reveals this truth. A car engine combusts fuel, releasing energy that pushes pistons and moves the vehicle forward. But at every moment, some of that energy dissipates as heat. The metal warms, the air stirs, the thermodynamic landscape shifts. And this dissipation is not a flaw in the design. It is a fundamental requirement. To produce motion, you must produce entropy. To create structure, you must break symmetry somewhere else. To harness energy, you must release some to the environment. If you listen closely, thermodynamics speaks with a calm authority. It says, all processes have a direction. All tasks have a cost. All ordered states will eventually give way unless energy flows in to maintain them. And this is why thermodynamics doesn't concern itself with microscopic chaos. It looks instead through a wider lens, focusing on what can and cannot happen on the grand stage of the universe. Perhaps the most astonishing implication is this: entropy decides which processes are physically possible. It is not mechanics or electromagnetism alone that dictates the unfolding of events. It is entropy that draws the boundaries around what nature allows. Water flows downhill because there are more ways for it to spread out than to gather at the summit. Heat flows outward because there are more ways for energy to be shared than concentrated. The world unfolds according to what is probable, not merely what is permitted by force. And perhaps you feel it too. This sense that entropy is not a dry concept trapped in equations, but a living principle that shapes our everyday lives. Every cooled cup of tea, every fading memory, every machine that warms as it runs. All of them are stories written in the language of thermodynamics. But just beneath this macroscopic story lies a deeper one, a more intimate layer of reality where molecules dart, collide, and rearrange in ways too small for the eye to see. Thermodynamics tells us that entropy increases, but it does not explain why at the level of particles. For that, we must descend into the microscopic world, where probability rules and motion never ceases. And so, as we close this gentle contemplation of heat and direction, perhaps it is time to lean in a little closer, to peer beneath the surface and follow entropy into the restless, shimmering realm of the microscopic world. Well, you see, as we drift from the grand, sweeping laws of thermodynamics into the microscopic realm, it feels a little like shrinking ourselves down to the size of a wandering dust mote, letting the ordinary world blur and dissolve until only the restless dance of particles remains. At this tiny scale, where atoms jitter and collide and drift in endless motion, entropy takes on a new texture. It is no longer just a rule of direction, or a constraint on engines, or the reason heat flows outward. Here, entropy reveals its true origins. It comes from movement, from possibility, from the countless configurations hidden beneath the stillness we think we see. Perhaps the first thing to understand is that nothing at this level ever truly rests. Even in the coldest winter night, even inside a solid block of ice, the molecules are trembling, vibrating, shifting ever so slightly. That subtle trembling is not a flaw in nature, but a fundamental feature of it. Motion is woven into the fabric of matter, and because particles never stop moving, they never stop exploring the space of possible arrangements. This ceaseless, jittering exploration is what gives entropy its microscopic meaning. You know, when you look at a glass of water, it appears calm, serene, a smooth surface reflecting light in quiet ripples. But beneath that surface, trillions upon trillions of molecules are racing about at incredible speeds, colliding with each other, rebounding, twisting into new configurations every fraction of a second. If your senses were fine-tuned enough to see this world, it would look less like a peaceful pond and more like a bustling metropolis at night. This hidden motion means that any macroscopic state, a glass of water, a block of metal, a puff of air, is actually a vast ensemble of microscopic possibilities, and entropy is the measure of how many such possibilities exist. Well, That leads us to a distinction that physicists whisper like a secret: the difference between the microstate and the macrostate. A macrostate is what we observe: the temperature of a room, the volume of a gas, the pressure inside a tire. These are broad, gentle descriptions, like saying a field is green without counting each blade of grass. The microstate, on the other hand, is the exact arrangement of each particle, its position, its velocity, its orientation. It is the detailed snapshot of the universe at the smallest imaginable scale. And here's the thing: there are countless microstates that correspond to the same macrostate. Take a box of gas. From the outside, we describe it with a few numbers: temperature, pressure, volume. But inside, the gas molecules are scattered in billions upon billions of possible configurations. Each configuration is a microstate. The macrostate, what we observe, is like a category containing each of these microstates, and some categories are far roomier than others. Entropy, in a sense, is the measure of how roomy a category is. A high entropy macrostate is one with many microstates. A low entropy macrostate has only a few. Perhaps the most astonishing part of this idea, is how it reframes the concept of disorder. At the microscopic level, disorder is not chaos in the emotional sense. It is simply the state that has the greatest number of configurations. There are many more ways for particles to be scattered than neatly arranged, many more ways for energy to be dispersed than concentrated. And because particles move randomly, unpredictably, they naturally drift into the states that occupy more space in the realm of possibility. This randomness is not noise or accident. It is the essential character of the microscopic world. Particles move according to probabilities, not certainties. A single molecule of air in your room is not following a script. It's wandering according to statistical laws, its path shaped by collisions with other molecules. And the more unpredictable the individual paths become, the more the entire system leans toward states that allow for greater freedom of arrangement. Imagine sprinkling a handful of tiny marbles onto a table. If you try to arrange them in a perfect grid, you must force them into place, adjusting each one. This state has low entropy because there are very few precise configurations that produce that perfect grid. But if you simply toss the marbles, letting them fall where they may, you generate a high entropy state, one with many possible arrangements. And the universe behaves more like the tossed marbles than the carefully arranged grid, not because it prefers disorder, but because disorder is simply more probable. And this insight is what allows entropy to act as a bridge between microscopic chaos and our everyday experience. When we feel a warm object cooling or watch perfume spreading through a room, we are not seeing a mysterious force at work. We are witnessing the collective behavior of countless particles drifting into states with more microstates available to them. The macroscopic behavior emerges naturally from the microscopic dance. In fact, microscopic randomness is the reason heat exists at all. Heat is not a substance or a fluid. It is the kinetic motion of particles. When something feels warm to the touch, it means the particles inside it are moving vigorously. When it feels cold, the particles are slower, gentler. And when heat flows from a warm object to a cold one, what is really happening is the transfer of microscopic motion. Particles collide, transferring energy until their motions blend into one shared rhythm. Entropy increases because there are many more microstates when energy is spread widely than concentrated in a single region. Perhaps, and this is the thing that always touches me, the entire macroscopic world, every breeze, every wave, every heartbeat, is built from these tiny, restless motions. We live in a universe where order emerges from chaos, where stability arises from motion, and where the invisible world of microstates shapes everything we see. It is humbling to realize that even the most serene moment, like a snowflake resting on your glove, is underpinned by molecules vibrating softly, never at rest. When physicists describe entropy as the link between microscopic probability and macroscopic outcome, they are acknowledging something profound. They are saying that the laws governing large-scale systems are rooted in the statistical behavior of countless tiny entities. The universe, in its deepest sense, is probabilistic. and entropy is the quiet bookkeeper of these probabilities, reminding us which states are common and which are rare. Now perhaps we can step back for a moment and reflect on something even deeper. If particles always move, always distribute their energy, always drift toward configurations with more possibilities, then it becomes clear why entropy tends to increase. It is not a command, but a consequence. Not an imposed law, but an emergent truth. Entropy rises because there are simply more ways for matter and energy to be spread than concentrated. The universe is exploring its own possibilities. One collision, one vibration, one microstate at a time. This microscopic perspective also reveals why a system that appears still is anything but. A cold block of metal looks motionless, but its atoms vibrate with thermal energy. A drop of water resting on a leaf seems frozen in time, yet its molecules are shifting and rearranging at unimaginable speeds. Stillness, you see, is an illusion created by scale, and entropy is the mathematics that converts this hidden movement into the macroscopic patterns we observe. As we explore this deeper connection, the role of statistical models becomes essential. Probability distributions, ensembles, and averages allow us to make sense of a world too complex to track particle by particle. We cannot follow each molecule individually, but we can describe the system's overall behavior with remarkable accuracy. And in doing so, we uncover a strange harmony between randomness and predictability. The microscopic world is unpredictable in detail, yet utterly reliable in aggregate. It's a little like listening to the roar of the ocean. Each droplet moves unpredictably, but the tide follows a pattern. Each particle behaves according to chance, but entropy follows a beautiful, steady curve. And so, standing at this strange crossroads between the tiny and the immense, you might begin to sense how entropy weaves the world together. It links the quivering dance of molecules to the grand flows of heat. It ties the microstate to the macrostate, the probable to the observable, the hidden to the seen. And perhaps this is where entropy reveals its true elegance. It transforms randomness into direction, chaos into meaning. But if all of this microscopic behavior shapes entropy, then what does this imply about the world we actually feel and remember? How does the ceaseless drift toward higher entropy shape not only heat and motion, but the very direction of time? Why does entropy give rise to the arrow of before and after, the difference between memory and possibility? Well, to understand that, we must take the next step. We must look beyond the dance of particles and follow entropy into its most mysterious role, the way it anchors the flow of time itself. Well, you see, when we finally reach the question of time itself, it feels as though the ground beneath our feet shifts a little, as if the world that seemed so stable, so obvious, suddenly reveals a quiet strangeness. We live inside time. We breathe it. We measure it. We feel it passing in our bones. And yet, when we look with the eyes of physics, the laws governing motion, electricity, gravity, even quantum fields, they do not care about direction. They run just as well forward as backward. But then, entropy enters the room, and everything changes. Entropy, this soft-spoken measure of possibility, becomes the only physical quantity that insists on a direction, and from that insistence, the arrow of time emerges. Perhaps the most surprising revelation is that time's one-way flow does not come from clocks or calendars, but from the statistical tendency of entropy to increase. You know, at the microscopic level, individual collisions between particles are reversible. If you filmed them and reversed the footage, no law would be violated. But when you gather trillions upon trillions of particles together, their collective behavior follows probability, not perfection. And probability leans, ever so gently, yet inexorably, toward states with more microstates, toward spreading, mixing, dissolving. That is what gives rise to the sense that time moves only forward, never back. Let's imagine something familiar. A glass shatters on the floor. Pieces fly outward, scattering in a chaotic pattern. Now imagine reversing that event. The shards leap from every corner, rising, aligning, forming the perfect contours of a glass before settling softly back into your hand. The reversed version is not forbidden by the fundamental equations of motion, but it is so extraordinarily improbable that the universe will not produce it spontaneously. Entropy has increased in the breaking. The number of accessible microstates exploded. For the glass to reassemble itself, the entropy would have to decrease dramatically. And that decrease, well, is simply too unlikely to ever happen in the lifetime of the cosmos. That is why, when we watch the backward footage of a breaking glass, something deep within us whispers, "No, that cannot be real." Our intuition about time is an intuition about entropy. We feel the direction of time because we feel the direction of increasing possibility. Perhaps this also explains another strange truth. We remember the past, but we do not remember the future. And that, is not merely a philosophical idea, but a physical one. Memory is a pattern, a structure. To remember something, our brain must form a specific arrangement of cells and molecules, a low entropy configuration. And such configurations can only form if energy flows into the system, if the environment around us increases in entropy to compensate. We build memories out of order, out of patterns carved against the backdrop of increasing disorder. The past is fixed because the entropy was lower then. The future is not yet written because its entropy has not yet grown into the vast space of possibilities. Perhaps you can picture it like this. Time is not a train we ride, but a valley we slide down. The landscape widens as we move forward, offering more ways for the universe to arrange itself. The further we go, the more possibilities there are, and so we never return upward, back to the narrow ridge of the past. And this is why the idea of rewinding time feels impossible. It would require every particle in the universe to retrace its steps with exquisite precision, aligning itself exactly as before. Even a single molecule of air drifting a different way would break the illusion. Entropy tells us that the path backward is too thin, too improbable, while the path forward fans outward into countless configurations. But perhaps the most beautiful part of all this is realizing that the arrow of time does not require consciousness. Time would flow even in a universe without observers, without memories, without language. The direction of becoming, past to future, is baked into the statistical architecture of physical law. Entropy increases because probability favors it. Time flows because entropy increases. We are simply passengers noticing the scenery. And once you see this connection, it begins to seep into everything. A melting ice cube is telling time. A cooling cup of tea is telling time. A spreading cloud of perfume is telling time. Every process that unfolds irreversibly is a clock of sorts, ticking away through entropy's arithmetic. Perhaps you've noticed how a photograph of the past captures a moment of lower entropy. A child's simple drawing. A pristine room before the party. A field untouched by footsteps. These images tug at us emotionally because they represent a world that was, for a fleeting instant, less spread out, less mixed, more improbable. Entropy gives weight to nostalgia. It wraps memory in a thin sadness because we know, deep down, that the past cannot be reclaimed. And yet, entropy is not cruel. It is simply the unfolding of possibility. Without entropy, nothing would change. No rivers would flow, no stars would shine, no life would arise. The arrow of time is not merely a consequence of disorder, but the engine that allows complexity to emerge. A universe stuck in perfect equilibrium would be a universe without story, without growth, without becoming. In this way, entropy shapes not only the direction of time, but its texture. The sense of before and after, the feeling of unfolding, the layering of moments into memory, all of it springs from this quiet statistical law. When entropy rises, the story advances. When entropy stalls, time feels frozen. And in a hypothetical universe of unchanging entropy, time itself would lose meaning. But perhaps the most profound thought is this: The arrow of time we experience is not universal. It is tied to the low entropy state of the early universe. Had the cosmos begun in a high entropy state, time as we know it would never have emerged. The flow we take for granted, the distinction between youth and age, between cause and effect, between remembering and imagining, these are gifts of an unlikely beginning. And as we follow this thread deeper, we stumble into a question so vast, it almost humbles the breath out of us. If the arrow of time arises because the universe started in a state of extraordinarily low entropy, then why did the universe begin that way? What set the initial conditions that allow time to unfold at all? Well, to answer that, we must lift our gaze from the microscopic dance of particles and look outward again, toward stars, galaxies, and the great architecture of creation. The arrow of time does not merely shape our memories, it shapes the cosmos itself. And so our journey must continue into the wide, glowing expanse of cosmology, where entropy becomes the storyteller, not of moments, but of the universe's entire destiny. Well, you see, when we turn our gaze from the small, restless dance of particles to the vast architecture of the cosmos, entropy does not fade into insignificance. If anything, it becomes grander, more mysterious, more deeply woven into the destiny of everything that has ever existed. It is almost poetic, really, how the same principle that governs the cooling of a cup of tea also shapes the birth of galaxies, the death of stars, and the far future of the universe. And that's the thing. The cosmos is not merely expanding in space, it is unfolding in entropy. Perhaps the first revelation, the one that feels almost unbelievable, is that the early universe, right after the Big Bang, was astonishingly low in entropy. A universe filled with hot, dense plasma might sound chaotic, but in terms of gravitational arrangement, it was remarkably smooth, almost perfectly uniform. And a uniform universe corresponds to low entropy because gravity prefers clumping. When matter gathers into stars, galaxies, planets, black holes, it moves into states with far more microscopic configurations. In other words, the early universe was like a pristine canvas, simple, symmetrical, full of potential. Over billions of years, entropy has been painting upon that canvas, giving rise to the structures we now see scattered across the night sky. And, this brings us to stars. You know, a star is not just a glowing sphere in the darkness, it is an engine of entropy. Deep in its core, nuclear fusion transforms hydrogen into helium, releasing extraordinary amounts of energy. Some of that energy escapes as light, warming planets, illuminating galaxies. But behind the light lies a deeper truth. Every fusion reaction increases entropy dramatically. The star, in shining, is quietly speeding the universe toward its higher entropy future. And when a star dies, well, that's when entropy surges. A supernova, that great cosmic blossom of fire and dust, takes the ordered core of a star and rips it apart, scattering matter in all directions. This violent dispersal dramatically increases the number of accessible microstates. A supernova is not only the death of a star, it is the release of entropy into the cosmic sea. Even the elements that make up your body, carbon, oxygen, iron, were forged in such explosions, born from entropy's handiwork. But even supernovae pale in comparison to the titans of entropy, black holes. Perhaps nothing in the universe feels as enigmatic, as quietly intimidating. A black hole concentrates mass into a tiny, dense region, yet paradoxically, it possesses enormous entropy. Why? Because there are unimaginable numbers of internal configurations consistent with a black hole's external appearance. We cannot see inside, but the surface, the event horizon, carries entropy proportional to its area, not its volume. Meaning, black holes are entropy giants. Cosmic reservoirs of possibility. They are the endpoints of gravitational collapse, the places where matter and information dissolve into the statistical ocean of curvature and quantum uncertainty. Some physicists even suspect that black holes may encode the entropy of entire galaxies. Perhaps the most haunting part of this picture is the far future. The universe is expanding, stretching space itself like a soft fabric. As expansion continues, matter becomes more dilute, stars burn out, galaxies drift ever farther apart, and entropy rises as energy spreads thinner and thinner, approaching a state known as thermal equilibrium, the so-called heat death or big freeze. In that distant era, eons beyond imagination, the cosmos would grow cold and dark, with entropy maximized. No temperature differences remain to drive processes. No new structures form. Only the faint afterglow of what once was. It is sobering, yes, but strangely beautiful too. A reminder that everything, every star, every life, every moment of warmth, is a temporary island of low entropy in a universe drifting toward equilibrium. Yet without that low entropy beginning, nothing could have existed at all. The swirling galaxies, the radiating stars, the delicate lattices of life, they all emerge from the universe's slow climb toward higher entropy. But perhaps the most fascinating thread is how cosmic structure itself arises from entropy's subtle guidance. Gravity, far from resisting entropy, actually accelerates it on cosmic scales. When a cloud of gas collapses under its own gravity, forming a star, entropy increases overall because the collapse releases heat into space. Even the majestic arrangement of galaxies, those shimmering webs stretching across billions of light years, formed because the low-entropy early universe allowed gravity to sculpt matter into intricate shapes. So you see, entropy is not merely the winding down of things. It is the architect of cosmic evolution. The universe began simple and grew complex, not in spite of entropy, but because of it. Every burst of starlight, every swirling nebula, every black hole spinning silently in the void, all of them are chapters in entropy's expanding story. And if we stand here, in the quiet twilight of 2025, and look up at the night sky, we are not just seeing stars. We are seeing entropy in motion. We are seeing the long thread stretching from the universe's pristine beginning toward its remote future. And perhaps, if we listen closely, we can hear the faint whisper of that story in the background radiation, in the nuclear burning of suns, in the collapsing hearts of dying stars, in the slow expansion of space. Yet even as entropy governs the cosmos on this grand scale, it also reaches into an entirely different domain, the realm of information. Because if entropy is about the number of possible configurations of matter and energy, then what happens when those configurations represent data, patterns, meaning? What does entropy tell us about the storage, transmission, and loss of information? And what does it mean that the universe itself might be, at some deep level, an information processing system? Well, to explore that mystery, we must step from stars and galaxies into the delicate mathematics of information theory, where entropy takes on a new and astonishing role. And that, naturally, leads us into the next chapter of our journey. Well, you see, when we shift from the vast, glowing architecture of galaxies into the quiet, almost whisper-like world of information, entropy does something rather astonishing. It changes clothes. It becomes not only a measure of physical disorder or cosmic unfolding, but a measure of uncertainty, of missing knowledge, of how many possible messages could be hiding behind the symbols we read. And perhaps that's the thing that makes this chapter feel so intimate. Because while cosmic entropy tells the fate of stars, informational entropy tells the fate of meaning itself. You know, it's humbling to realize that every conversation, every sentence, every pixel glowing on your screen right now is part of a delicate dance between order and uncertainty. Information, in a deep sense, is pattern. It is structure imposed upon the swirling sea of possibilities. And when structure becomes blurred, when signals lose clarity, entropy rises. In this abstract domain, entropy is no longer about particles but about choices, about the number of messages that could plausibly produce the data we see. Perhaps a simple example helps. Imagine you're listening to a faint radio signal late at night. Static hums in the background. Some words come through clear, others dissolve into noise. The less certain you are about what you've heard, the higher the informational entropy of that signal. It's not that the universe dislikes clarity, it's just that clarity requires resistance against entropy, whether in physics or in communication. And this connection between information and entropy was one of the great revelations of 20th century science. Claude Shannon, with a kind of mathematical elegance, revealed that the entropy of a message is proportional to the number of possible interpretations it could take. If a message is perfectly predictable, if you know every letter before you read it, its entropy is low. But if every symbol could be several different things, if the stream of data is bursting with possibilities, the entropy rises. In a way, informational entropy is a measure of surprise. The more unexpected a symbol is, the more information it carries. Think of a book filled only with the word yes, repeated across every page. You would stop turning the pages after a moment. There is no real information there, no novelty, but introduce uncertainty, different letters, different word choices, and suddenly the story becomes rich. Entropy becomes the companion of meaning. You see, this is why compressed files are smaller. When you compress data, you remove redundancy, squeezing out predictable patterns. You reduce entropy by reorganizing information into a more efficient form. A zipped file, quietly sitting in your computer, is a portrait of low informational entropy. It is neat, precise, condensed, but the moment you decompress it, the entropy blooms again, expanding back into its original multiplicity of symbols. Compression is not magic, it is entropy management. But, as with every domain touched by entropy, there is a price. When data becomes noisy, when bits flip, when signals distort, the entropy rises. Noise adds uncertainty. It injects randomness into patterns that once carried meaning. And if the noise becomes too great, the message dissolves, replaced entirely by entropy. Communication becomes impossible. You know, every technology we rely on today, every satellite transmission, every video you stream, every word whispered across a phone line, must battle entropy. Error-correcting codes, redundancy checks, signal amplifiers, all serve the same purpose: to keep noise at bay, to resist the rise of informational entropy long enough for meaning to survive its journey. And, perhaps one of the most remarkable insights is that storing information requires energy. Whenever you save a file, write a text, draw a picture on your tablet, you are lowering entropy in one region of your device by arranging bits into a specific pattern. But the universe demands compensation. Somewhere else, usually in the form of heat released by your computer, entropy must increase. Even erasing a file generates heat, because destroying information releases entropy back into the physical world. This relationship between information and thermodynamics is not metaphorical. It is physical, literal, unavoidable. A computer chip warming beneath your fingertips is a tiny demonstration of the second law of thermodynamics. Each logical operation creates microscopic irreversibilities. In that sense, your computer is a little engine, not just of computation, but of entropy. And if we follow this thread deeper, well, we find ourselves facing one of the most profound insights of modern physics. Information cannot be separated from the physical world. It is not abstract in the way we once thought. Every bit of information, every choice between yes and no, every pixel, illuminated or dark, has physical consequences. Information is embodied. Its presence or absence affects entropy. This is why some physicists propose that the universe itself is, in some mysterious way, an information processing structure. The patterns we observe, galaxies forming, particles colliding, life evolving, may be the visible expression of information shaping matter. And entropy, always rising, represents the gradual dispersal of information into forms that are harder and harder to retrieve. Perhaps this explains why losing information feels devastating on an emotional level. When a photograph fades, or a memory dims, or a story is forgotten, we experience not only psychological loss, but a kind of informational entropy. The pattern dissolves, the uncertainty grows, meaning becomes unreachable, and the universe, quietly and without ceremony, moves one step closer to equilibrium. And yet, perhaps we should not despair, because information, like matter and energy, can be reorganized, transformed, encoded. We compress it, protect it, replicate it. Life itself, after all, is a battle against informational entropy. DNA stores the patterns of existence. Cells repair themselves, copying information faithfully. But even then, mutations creep in. Noise slips through. Entropy never disappears. It only waits for its turn. You know, as we move deeper into the digital age, into 2025 and beyond, we are surrounded by an explosion of data. Vast oceans of information flow across the globe every second. But this explosion comes with consequences. Data centers warm the night air with the heat of computation. Servers hum like metallic beehives. Every stored bit, every transmitted signal, every erased log carries a thermodynamic cost. In that way, information entropy reminds us that knowledge is not free. Meaning is not effortless. Every piece of order in our digital world must be maintained, protected against noise. And sometimes we feel that effort in our daily lives, when files become corrupted, when networks slow down, when devices overheat. These are not flaws. They are small echoes of the universe's fundamental laws, expressing themselves through our technologies. But the relationship between entropy and information becomes even more intriguing when we ask a deeper question. If entropy measures uncertainty, then what does it mean to know something? When we learn, are we reducing entropy within our minds, carving structure from the haze of experience? And when memories fade, when names slip away from us, is that entropy creeping back in? Perhaps, and perhaps not. But the symmetry is hard to ignore. Patterns once lost are costly to regain. And stored information, whether in a computer or a human mind, requires energy to maintain. Learning is not free. Remembering is not free. Even thinking has a thermodynamic footprint. And this brings us, gently and inevitably, to an idea that feels strangely poetic. Entropy is a measure of possibility, and information is the art of narrowing those possibilities into meaning. To know something is to reduce the uncertainty of the world. To forget is to let uncertainty bloom again. As we linger here, between physics and cognition, between data and thermodynamics, a compelling question begins to form in the air. If information must fight entropy to persist, then what happens in the messy, unpredictable realm of everyday life, where systems constantly slide toward disorder unless energy flows in to keep them stable? How does entropy shape not only the stars above us and the data we store, but the rhythm of our own daily existence? Well, that question leads us into a more familiar terrain, the world of homes, bodies, routines, and the gentle unraveling of things around us. And so, naturally, our journey continues into the next chapter, where entropy steps out of the laboratory and into the fabric of ordinary life. Well, you see, when we bring entropy down from the stars and let it step gently into the world of our daily lives, something quite tender happens. The universe suddenly feels closer, less like an abstract expanse of equations and more like a quiet companion sitting beside us, reminding us that the laws shaping galaxies are the very same laws shaping the clutter on our desks, the food in our refrigerators, the warmth of our bodies, the air drifting softly across our skin. And that's the thing. Entropy is not distant. It's intimate. It unfolds in our homes, our habits, our breath. Perhaps the most familiar example is a room that never stays tidy on its own. You know this feeling well. You clean it, everything placed just right. And then, slowly, almost imperceptibly, objects drift out of place. A book left on the table, a shirt casually draped over a chair, a cup forgotten on the windowsill. Nothing dramatic, just the natural slide toward higher entropy. The room becomes messy without anyone intentionally making it messy, because disorder has many more possible configurations than order. It's not personal, it's statistical. And then, of course, comes the opposite experience. When you want the room to return to order, you have to put in energy, your energy. Picking up clothes, stacking books, wiping down surfaces. Reducing entropy costs effort because you are creating structure, imposing a pattern where the natural drift prefers looseness. And perhaps this is why cleaning feels tiring not only physically, but philosophically. You are quietly wrestling with the universe's most patient law. But entropy does not stop at rooms. It touches food, too. A fresh piece of fruit, firm and sweet, is a small miracle of low entropy. Cells ordered, molecules structured, energy captured in delicate bonds. Leave it on the counter long enough, though, and it softens, darkens, breaks down. Oxygen seeps in, microbes flourish, molecules rearrange, and slowly the fruit moves toward higher entropy. Spoiling is just the microscopic world exploring its own possibilities. And yet, despite knowing this, there's still a sadness in watching something once so vibrant drift away into disorder. Entropy often wears the mask of time. Even something as gentle as scent reveals entropy at work. Spray perfume in one corner of a room, and the molecules drift outward, spreading until every corner carries the faint trace of fragrance. Why does the smell never spontaneously gather itself back into the bottle? Because that would require a massive decrease in entropy. It's not forbidden by physics, but it's so impossibly improbable that you could wait longer than the age of the universe and never see it happen. Diffusion is just probability making itself visible. And then we come to ourselves, our living, breathing bodies. Life, in a sense, is constant work against entropy. Inside you, countless processes are happening every second to maintain structure, to keep the body from drifting into the equilibrium of stillness. Cells repair themselves, enzymes build molecules, energy flows into every corner of your being. The reason you must eat is not only to fuel movement, but to fuel order, to keep entropy at bay. Because if your body stops investing energy into maintaining its structure, entropy quickly rises, and life, in its delicate balance, fades. But even when the body is functioning beautifully, entropy makes itself known through heat. Every cell that does work produces a little energy that must be released as warmth. And your body has a clever way of handling that. Sweat. Perspiration is not merely a response to heat, but a thermodynamic necessity. Through evaporation, your body transfers entropy into the environment, preserving its own internal balance. You sweat not because you are weak, but because life requires the export of disorder. Machines behave the same way. A refrigerator, for example, feels like a machine that creates cold, but that is not quite true. It doesn't create cold, it moves heat. It pumps entropy out of its interior and releases it behind the machine, into your kitchen. The inside becomes more ordered only because the outside becomes slightly less ordered. The balance sheet remains intact, and if you've ever stood near the coils at the back of the refrigerator, you feel the warmth that is the cost of that local order. In fact, all cooling machines, air conditioners, freezers, climate systems, are entropy pumps. They produce cold in one region by expelling heat into another. Your air conditioner makes your room comfortable, but it also warms the world outside just a little more. Entropy never disappears, it simply moves. And this theme repeats itself in every aspect of daily life. The more order you want in one place, the more entropy you must release somewhere else. This dance is not a flaw, it is the rhythm of nature, and once you begin to notice it, you see entropy everywhere. Perhaps you've lived through the experience of preparing a meal, watching ingredients arranged neatly at the start, clean vegetables, bowls of spices, measured grains, everything structured, everything ready. Then, as cooking unfolds, counters grow, cluttered, wrappers appear, bowls stack up in the sink. The act of creating a structured dish produces disorder around it. Creativity and entropy rise hand in hand. Or think of laundry. You fold clothes into crisp geometric shapes. They stack neatly, almost like little monuments to low entropy. But wear them. Toss them into a basket, and the structure dissolves. Not because you wished it so, but because entropy prefers freedom over constraint. And then, there is the entropy of smell, which spreads through rooms and streets, through kitchens and autumn forests. The scent of bread baking travels outward because mixing is statistically more likely than unmixed stillness. The aroma of rain on dry earth rises and diffuses because molecules wander. If you stand quietly and breathe deeply, you are inhaling tiny traces of entropy unfolding in the world around you. Entropy even shapes weather, wind patterns, temperature gradients, cloud formation. A storm is not chaos in the emotional sense, but a redistribution of energy, a system adjusting toward equilibrium. Weather is the Earth's way of negotiating its own entropy balance. Yet perhaps the most profound expression of entropy in daily life is the aging of objects. Metal rusts, paint fades, plastic becomes brittle. The world gently unravels, matter rearranges itself, exploring higher entropy states. And through this slow drift, time becomes visible. But there is something beautiful in this too. Entropy gives life its texture. Rooms that never grew messy would feel sterile. Food that never changed would be lifeless. Bodies that never warmed or cooled would not be alive. Even the bitter sweetness of seeing things age is tied to entropy's unbroken conversation with time. And you know, this everyday entropy hints at something deeper, a thread that ties kitchens and living rooms to cell membranes and neurons. Because if entropy shapes the messiness of daily life, it must surely shape the delicate order of living organisms too. Life is a small miracle of defiance, holding pockets of low entropy against the universe's drift. But how does life manage such a feat? How do cells, tissues, and entire ecosystems maintain their improbable structures? Well, to answer that, we must follow entropy into the intricate world of biology, where life survives by dancing, bravely, beautifully, against the current of disorder. Well, you see, when we step from the gentle disorder of everyday life into the intricate machinery of living things, entropy takes on a new and almost paradoxical role. Life, in all its trembling delicacy, seems to stand in defiance of entropy. A tree grows upward against the pull of gravity. A cell repairs itself. A living body maintains astonishing internal order despite the constant tug of randomness. And yet, life does not break the laws of thermodynamics. It survives by obeying them, by mastering them even, through a beautiful exchange of energy and entropy with the environment. And that's the thing. To live is to resist entropy locally, while releasing even more entropy globally. It's a quiet negotiation with the universe, renewed moment by moment. Perhaps the clearest way to see this is to imagine a single cell, floating gently in a drop of water. Inside it, molecules are arranged with exquisite precision. Proteins fold in particular shapes, membranes arch like sculpted walls, DNA coils neatly into its labyrinthine code. The cell's order is fragile but persistent. It must constantly invest energy to hold on to this order, because the natural drift of entropy would dissolve these structures if the cell ever stopped working. Life is not a static state. It is a process, a continuous maintenance of improbably low entropy against the backdrop of a universe that prefers spreading, mixing, and erasing distinctions. You know, from the moment we are born, every living organism begins a long conversation with entropy. We take in energy so that we can push back against disorder. Plants gather sunlight, building sugars from carbon dioxide and water. Animals eat plants or other animals, reclaiming stored chemical energy. No creature exists on its own. Life is a relay where each organism borrows energy from somewhere else in order to remain structured just a bit longer. Without that flow of energy, entropy rises quickly inside the body, and the delicate balance unravels. And then there is the body's most haunting threshold, death. When an organism dies, the flow of energy stops. The biochemical circuits shut down. The cells that once repaired damage, removed toxins, assembled proteins, all of them grow silent. And without this constant maintenance, entropy rushes in. Structures lose coherence, molecules drift apart, tissues break down. Death is not merely the end of life. It is the moment entropy finally claims the order that energy once held in place. The body moves toward its maximum entropy state, and in doing so becomes part of the natural cycles that sustain other life. Yet while we live, our bodies perform incredible feats to resist this fate. Cells repair themselves. They fix DNA errors, rebuild membranes, refold proteins. These acts of repair are not miracles. They are entropy management. Damage is the creeping rise of disorder. Repair is a small, determined push in the opposite direction. Every time a cell corrects a mistake, it uses energy to reduce entropy internally while exporting heat and disorder into the world around it. Digestion, too, is a conversation with entropy. When we eat, we are not simply filling our stomachs. We are taking complex molecules, rich in structure and low in entropy, and breaking them down into simpler components. This release of energy allows us to build our own low-entropy structures. The process increases entropy globally, even as it gives us the power to maintain order within ourselves. In a sense, every meal is a negotiation. We trade entropy gained in the environment for the right to keep entropy low inside our cells a little longer. Then there is the brain, the hungriest organ of all. It consumes a remarkable amount of energy, far more than its size might suggest. Why? Because thought itself is a form of order. Patterns of electrical activity must be maintained, synapses must regulate signals, chemical gradients must be upheld. The brain is a masterpiece of low entropy that requires constant energy to preserve its structure. And when the energy flow falters, through exhaustion or illness, our thoughts grow foggy. Entropy whispers at the edges of consciousness. And perhaps the most astonishing symbol of biological order is DNA. This long molecule, curled gently within the nucleus of every living cell, contains instructions, information that resists randomness with stubborn precision. DNA is like a quiet library, holding the patterns that make life possible. But even DNA is not immune to entropy. Errors slip into the sequence. Radiation breaks strands. Reactive molecules cause mutations. And yet, life responds with extraordinary repair systems, scanning, correcting, stitching the code back together. These repairs, too, cost energy. Order is expensive, and life pays the price willingly for as long as it can. And, if all of this seems like a contradiction, life fighting entropy while entropy ultimately wins, it might help to remember that nothing in biology violates the laws of thermodynamics. Life creates pockets of order precisely by increasing entropy around it. A plant builds a leaf by capturing sunlight and releasing heat. A human grows by eating food and releasing waste. The overall entropy of the universe still rises, but within that rising tide, small islands of order can form and persist. Life is one of those islands, maybe the most beautiful one we know. What's more, entropy shapes evolution itself. Mutations, tiny increases in entropy, introduce randomness into DNA. Natural selection then identifies which changes lead to stable forms of order that can survive. Evolution is not a march toward perfection. It is a long interplay between randomness and structure, between entropy and adaptation. Life emerges from the tension between these forces, sculpted by chance and refined by survival. Even ecosystems behave like entropy balancing networks. Forests, oceans, grasslands, all of them distribute energy, recycle matter, and maintain structure while exporting entropy into the environment. The complexity of life on Earth is a testament not to the defeat of entropy, but to the extraordinary ways living systems channel it. And perhaps once we see life this way, something subtle shifts in us. We begin to notice the fragility of order, how much energy it takes to keep a body warm through winter, to grow food from soil, to heal after illness. We understand why fatigue feels heavy. The body is spending enormous energy against a tide that never stops rising. We feel more tender toward the living things around us, each one a small miracle of organization held briefly against the universal drift toward simplicity. But there is still a deeper question stirring beneath all this. If life is a local rebellion against entropy, how do we reconcile that with the paradox that entropy shapes the arrow of time itself? How can living organisms, which seem to move against entropy locally, exist in a universe where entropy always increases globally? And what happens when we encounter phenomena so strange that they seem to challenge the very laws we have been studying? Well, to explore those puzzles, to walk into the territory where entropy meets paradox and imagination, we must step next into the realm of thought experiments and illusions, those curious corners of physics where our intuitions falter and entropy reveals its most subtle mysteries. Well, you see, as we arrive at the realm of paradoxes, those curious borderlands where entropy seems to twist, shimmer, and challenge our intuitions, we begin to sense that the universe is not simply a machine ticking predictably forward. It is also a storyteller, offering puzzles that force us to think more deeply about what disorder, probability, and irreversibility truly mean. And perhaps that's the thing. Entropy becomes most fascinating precisely where it seems to wobble, where our everyday expectations collide with the counterintuitive beauty of physical law. Let's begin with perhaps the most iconic paradox of all, Maxwell's demon, a tiny creature imagined by James Clerk Maxwell, perched atop a partition dividing a box of gas. With exquisite agility, the demon opens and closes a tiny door, sorting fast-moving molecules to one side and slow-moving ones to the other. Over time, one chamber grows hotter and the other colder. It seems at first glance as though the demon has decreased entropy without spending energy, a violation, a rebel, a loophole in the second law. And when you first hear this, well, it is tempting to think the demon exposes a crack in the armor of thermodynamics. But the deeper you look, the more the illusion dissolves. The demon must observe, record, decide, and act. Each of these processes carries costs. Information must be stored and erased. Decisions must be encoded. And as we learned in earlier chapters, information is physical. Storing it, and especially erasing it, generates entropy. The demon is not magical. It is bound to the same physical laws as everything else. So while it lowers entropy in one place, it increases it elsewhere, ensuring the second law holds firm. The paradox becomes a lesson. Entropy is never defeated. Sometimes it is simply redistributed. This idea that reducing entropy locally always requires increasing it somewhere else is profoundly important. It reveals a kind of cosmic bookkeeping, a balance that cannot be cheated. A refrigerator lowers entropy inside its cool interior, but raises entropy outside. A living organism maintains intricate structure only by releasing waste heat and disorder. Maxwell's demon, too, must pay for its work. No matter how clever we imagine the mechanism, the cost remains. And this leads naturally to another class of paradoxes, processes that seem to reverse entropy, but only because we are not looking widely enough. Consider those famous laboratory demonstrations where particles appear to unmix, where a fluid briefly becomes more ordered. These phenomena often arise in tiny systems, over very short timescales. At the microscopic level, randomness occasionally runs backward, not because entropy is violated, but because probability allows fluctuations. For a brief moment, particles may cluster more tightly, or energy may concentrate by chance. But these events are rare and fleeting. Zoom out, and the trend is unmistakably upward. Entropy on average still increases. It is a bit like tossing a handful of coins. Occasionally, improbably, you might get all heads. But over thousands of tosses, order from randomness becomes vanishingly rare. Entropy offers a direction not because reversals are impossible, but because they are overwhelmingly improbable. Time flows forward on the river of statistics. Perhaps you've seen the example of a drop of cream swirling into a cup of coffee. Moments before mixing, the boundaries are distinct, dark coffee separated from pale cream. Then, with a stir, the colors merge into a smooth gradient. Try as you might, you cannot unstir the cup. But imagine, for a moment, watching the video of that mixing process played backward. The cream would leap from all corners of the cup into a beautiful, organized ribbon. It looks like magic. But the reason such a reversal never happens is simple. There are vastly more microscopic ways for the fluids to be mixed than separated. Mixing is easy, natural, probable. Unmixing requires an arrangement so precise it is, for all practical purposes, unreachable. And this, leads us to the impossibility of perpetual motion, machines that run forever, creating work without consuming energy or producing waste heat. Humanity has dreamed of such machines for centuries, but in the world governed by entropy, they are fantasies. A machine that extracts energy without producing entropy would be like a river flowing uphill, or like cream unmixing from coffee without intervention. Every real engine produces some waste heat. Every real process increases entropy somewhere. The longing for perpetual motion is, in a sense, a longing to reverse time, to restore what has been lost, to reclaim energy without paying the thermodynamic price. But nature tells us softly, no, there is no free lunch. Order is costly. Structure requires effort. Even the universe itself cannot escape its long drift toward equilibrium. At this point, perhaps another paradox emerges, one that is not mechanical, but philosophical. If entropy cannot be reversed completely, then why does the world feel so full of structure? Why do snowflakes form? Why do galaxies spin? Why does life persist? Shouldn't everything already be a uniform haze? The answer lies in the fact that entropy governs the direction of change, not the richness of the journey. Structures emerge not despite entropy, but because of the flow of energy through systems. A snowflake forms because water molecules shed heat as they arrange into crystalline order. Hurricanes arise because warm oceans release energy into the atmosphere. Stars ignite because gravity causes matter to clump and release heat. All of these processes increase entropy overall, even as they create local pockets of astonishing order. So we encounter yet another apparent paradox, order, born from entropy's rise. But in truth, there is no contradiction. Entropy does not forbid complexity. It simply requires that complexity be purchased with the currency of increased disorder somewhere else. And then there are the more subtle, modern paradoxes of physics, those that sit at the edges of theory. Thought experiments involving memory, black holes, quantum information, and time reversal. Many of them sound like violations of entropy at first blush, but the more deeply physicists investigate, the clearer it becomes that entropy is resilient, woven into the mathematics of both classical and quantum worlds. When a paradox appears, entropy is usually waiting just beneath the surface, offering a resolution. For example, in some quantum experiments, tiny particles appear to behave in ways that seem to rearrange information without cost. But when we include the measurement devices, the environment, and the entire system, entropy remains consistent. In quantum thermodynamics, entropy can even be shared, entangled, or moved around, but never destroyed. Even when we step into the strange landscape of mixing fluids, coffee and milk, ink and water, the impossibility of unmixing is not because physics forbids it, but because it requires an astronomically precise coordination of all molecules involved. Complexity is fragile. One misplaced atom ruins the reversal. That fragility hints at something deeper. Entropy is not merely a law, but a measure of how unimaginably large the microscopic world is. It speaks to the overwhelming tide of probability. Even if entropy could momentarily reverse, it is so unlikely that the universe itself would age and fade long before such a fluctuation ever occurred on human scales. These paradoxes remind us that physics is not just a collection of rules, but a dialogue between what is possible and what is probable. Entropy sits between the two, marking the boundary. And as deeply as we study it, even here in the quiet hours of 2025, there are still riddles that beckon us forward. New models of entropy in quantum computing, new theories of information in black holes, new ideas about how randomness and order shape one another. Physicists continue to probe these mysteries not because entropy is fragile, but because it is so very fundamental. And perhaps this is the moment where we step back and notice a gentle truth. These paradoxes are not mistakes or failures in theory. They are invitations. Each one asks us to refine our understanding, to look more broadly at the system, to see that entropy never decreases without being compensated elsewhere. It is a global law masquerading as a local mystery. But if entropy governs paradoxes, and if it shapes both life and cosmic evolution, then what happens when we channel it into our inventions? How does entropy influence the machines we build, the technologies we rely on, the digital world humming quietly all around us? Well, to explore that question, to see entropy not as an adversary of engineering, but as its silent architect, we must now step into the realm of technology itself, where every device, every engine, every line of code carries the unmistakable signature of entropy. Well, you see, when we step across the threshold from paradoxes into the humming, glowing, buzzing world of human technology, entropy reveals itself not as a distant cosmic law, but as a quiet engineer sitting inside every device we build. It is there in the warmth of your phone after a long video call, in the soft hum of a server room deep beneath a city street, in the faint whirring of a laptop fan trying its best to push disorder outward so the machine inside can keep working. And that's the remarkable thing. Technology does not escape entropy. Technology runs on entropy. Every line of code, every rotating gear, every spark of electricity is shaped by it. Perhaps the simplest truth is this: all machines create entropy, not because they are poorly designed, not because humanity hasn't discovered the right materials yet, but because doing work, any work, requires energy to flow, and wherever energy flows, entropy follows. A car engine, for example, burns fuel to move pistons, but it also heats the hood, the air, the exhaust pipe. That heat is entropy being released. A wind turbine spins, converting the graceful motion of air into electricity, yet even turbines warm slightly as their gears turn. Friction, dissipation, microscopic irreversibilities, entropy again. Even the most advanced machines in the world, the ones hidden inside clean rooms, assembled by robotic arms, cooled by liquid nitrogen, still bow to entropy's arithmetic. Efficiency has limits. Heat accumulates. Energy disperses. Engineers can delay entropy, redirect it, harness it, but never erase it. And, this leads us to one of the fundamental truths of modern engineering. The efficiency of any engine or machine is bound by entropy. There is a maximum theoretical efficiency for converting heat into work, and no design can cross that boundary. This is why no car engine, no power plant, no jet turbine can ever be 100% efficient. Some of the energy always becomes entropy. It becomes heat you cannot use, a whisper of disorder that slips beyond the grasp of mechanical purpose. Perhaps nowhere is this more striking than in the quiet, glowing cores of data centers, those colossal digital cathedrals where the world stores its memories. Each rack of servers hums with activity, processing information, routing signals, training artificial intelligence models. But the more computation occurs, the more heat the machines produce. And that heat must be pushed away, vented, dissolved into the environment. The data center becomes a furnace of information and entropy intertwined. Cooling these facilities is not a trivial matter. Engineers spend fortunes designing airflow systems, coolant loops, evaporative towers, subterranean heat exchangers, all to counter the heat created by machines doing work. This challenge is not a flaw of technology. It is the second law of thermodynamics made visible in the real world. Every bit flipped in a processor, every mathematical operation, every pixel illuminated on a screen adds entropy to the environment. And you know, as artificial intelligence grows more powerful, as servers become more densely packed, as processors reach unimaginable speeds, the heat they produce increases accordingly. More computation means more entropy. And so the cooling systems must grow more sophisticated. They become silent battles fought between engineers and the inevitability of physics, with entropy always having the final word. Even the batteries in our devices, the little chemical hearts that power our phones, laptops, and electric cars, age because of entropy. Inside a battery, ions move, Electrodes degrade, chemical structures loosen. With each charge and discharge cycle, microscopic disorder increases. The battery loses capacity, not because something attacks it, but because entropy slowly reshapes its internal landscape. It is humbling, perhaps, to realize that a dying battery is simply an echo of the universe's fundamental tendency to explore new configurations. Disorder spreads, structure weakens. Even the technology we rely on every day is not immune to the march of entropy. It ages, it warms, it drifts unpredictably. Entropy is its invisible companion, and yet technology thrives because we learn how to manage entropy, not eliminate it. Engineers design heat sinks, cooling fins, thermal pastes, ventilation grids, all dedicated to carrying entropy away from delicate components. A smartphone's metal frame is not just aesthetic, it is a cooling surface, a physical bridge for entropy to escape. A laptop's fan is a mechanical sigh, exhaling disordered energy into the air. Even cables and connectors are shaped by entropy's demands. Data traveling down a wire generates heat through resistance. Fiber optic cables reduce this heat but cannot eliminate it. Every signal sent, every byte transferred carries a thermodynamic cost. And if we look even deeper, we find that artificial intelligence, high-speed computing, and quantum processors all face the same fundamental challenge: managing entropy. A computer chip operates with billions of switching events every second. Each switch creates a tiny bit of heat, and as chips become smaller and faster, their ability to dissipate heat becomes more difficult. Engineers race to find new materials, new geometries, new cooling methods, but entropy's pressure never relents. Even future technologies, quantum computers, photonic processors, molecular machines, cannot escape entropy. They might distribute it differently, conceal it more elegantly, channel it with greater efficiency, but they still generate it. They must. The universe allows no exceptions. This is why perpetual computing, like perpetual motion, remains impossible. A machine that performs infinite computation without generating heat would violate the second law. It would require an entropy-free operation, and such a thing, as appealing as it sounds, is forbidden by the fabric of physics. But perhaps this doesn't limit us, it inspires us. Because once you accept that entropy is part of every technology, you begin to notice a kind of beauty in the way machines and thermodynamics dance around each other. A power plant is a giant choreography of heat and work. An electric motor is a whisper of entropy made useful. A refrigerator is a thermodynamic pump sculpting order in one region while releasing disorder in another. Even the quiet glow of your phone screen is a conversation between electricity, heat, and entropy. And this, you see, brings us to another truth. Loss of energy is inevitable. No system can operate without losing some of its energy to entropy. Cars burn fuel. Power lines warm the air. Batteries degrade. Servers heat rooms. Nothing in the technological world escapes this law. We can minimize losses, but never remove them entirely. Yet, remarkably, this inevitability has not stopped human innovation. If anything, it has fueled it. Engineers understand entropy intimately. They design around it, they harness it, they turn it into opportunity. Waste heat from factories warms nearby buildings. Data center heat is used to grow vegetables in greenhouses. Electric cars regenerate energy through braking, capturing a bit of entropy's drift and converting it back into useful work. Entropy becomes not an enemy, but a collaborator, a quiet guideline shaping the boundaries of what technology can do. And perhaps this is where the story of entropy feels most human. Technology, after all, is our attempt to create order, to impose structure on the world, to build tools that resist entropy locally, even while increasing it globally. A smartphone organizes information. A house organizes space. A medical device organizes biological data. But maintaining these pockets of order requires energy, maintenance, and, inevitably, entropy. Every invention is a temporary defiance of disorder. A light bulb shining in a dark room. A computer organizing billions of bits of data. A satellite maintaining its orbit while radiating waste heat into the void. Entropy does not forbid these achievements. It simply demands that we pay the thermodynamic cost. And well, Once we accept this cost, something profound happens. We begin to see our technologies not as perfect tools, but as fragile structures woven against the tide of disorder. We appreciate the elegance of a machine that runs smoothly despite entropy's insistence. We marvel at how engineers coax order from chaos, and we sense, perhaps for the first time, that technology is not separate from nature, but deeply embedded in the same physical laws that govern stars, storms, and living cells. But if entropy guides our machines, if it shapes how technology grows, ages, and dissipates energy, then what does this say about us? About our meaning, our place in the universe, our quest for understanding? If entropy is the backdrop of existence, then how do we find purpose within a world where all structures eventually fade? Well, to explore that question, to step beyond physical law and into the realm of human meaning, we must continue our journey into the philosophical heart of entropy, where science and reflection intertwine. Well, you see, when we finally arrive at the philosophical edges of entropy, something quiet settles over the mind, as though the universe, after revealing its equations, its probabilities, its stellar furnaces and microscopic dances, now leans in and asks a softer question. What does all of this mean for us? For beings who love, who remember, who build, who hope. Entropy is not only a scientific principle, it is a lens through which existence itself becomes strangely, achingly clear. And that's the thing. Once you understand entropy, you begin to see life, beauty, even meaning, in an entirely new light. Perhaps the first philosophical truth entropy whispers is this: order is temporary. Every structure we admire, a cathedral, a snowflake, a human face, exists only as a brief eddy in the great river of disorder. Entropy assures us that all forms eventually loosen, dissolve, drift apart. And this could feel bleak, but somehow, when we sit with it long enough, it becomes strangely tender. Because if order is fleeting, then every moment of it becomes precious. A sunrise, a child's laughter, the symmetry of a shell, the turning of a page. These moments are improbable arrangements, tiny triumphs against the vastness of possibility. And perhaps that's where entropy touches the heart. It teaches us to value the temporary. The fragility of things is not a flaw. It is the very source of their beauty. Well, consider this idea. Every beautiful structure you've ever seen is a moment of low entropy. A flower blooming, a drifting snowflake, a city at dusk, lights flickering on like constellations. These are pockets of order sculpted by energy flowing through systems. They exist precisely because entropy increases overall. They are the intricate curls of foam on the wave of universal disorder. Without entropy rising, none of this complexity would exist. So beauty is not an exception to entropy. It is born from it. But here is where the universe becomes quietly profound. Human consciousness, with all its memories and emotions, creates the sensation of order in a world that trends toward disorder. You see, the mind is a pattern-finding engine. It takes the chaos of sensory input and sculpts it into meaning. It gathers fragments, sounds, colors, textures, and weaves them into coherent stories. Entropy may rule the physical world, but awareness creates islands of internal structure. Consciousness, in a strange way, is our species' attempt to hold back the tide, even if only in the realm of perception. And yet entropy reminds us that even these inner structures shift. Memories fade, feelings soften, understanding deepens or dissolves. The mind itself is not immune to the slow drift toward disorder. And still, we continue to create meaning, again and again. Perhaps that resilience is one of the most beautiful forms of order the universe has ever produced. Civilizations, too, are temporary arrangements of low entropy. Languages developed, cities built, knowledge recorded. All of it requires tremendous energy to maintain. Societies must work constantly to resist disorder. Roads crumble without repair. Laws decay without human attention. Stories vanish without retelling. And so civilization is not a permanent triumph over entropy, but a continuous effort, a collective exhale of energy into the future. But rather than making civilization seem fragile, this truth reveals something astonishing. The fact that it exists at all, even for a while, is a miracle of coordination, a symphony of human intention playing against the quiet background hum of disorder. Entropy shows us that every achievement, scientific, artistic, cultural, is not merely impressive, it is cosmically improbable. And that improbability is what gives it weight, meaning, and wonder. And if entropy assures us that all structures eventually fade, it also invites a deeper appreciation for the present. Because the awareness that the universe is always moving toward greater disorder makes every fleeting configuration more poignant. A candle flickering, a ripple in a pond, a friendship, a moment of stillness in a noisy world. These things matter because they are temporary. Entropy is the soft reminder that nothing lasts forever, which is precisely why everything matters now. In that sense, entropy becomes a quiet teacher of gratitude. But perhaps the most profound philosophical question entropy raises is this: if everything tends toward disorder, then what is the purpose of striving for order at all? Why build, create, love, preserve, if entropy will eventually undo everything? And maybe the answer is simply this: meaning is not found in permanent outcomes, but in temporary acts of creation. The universe does not ask us to defeat entropy, only to dance with it. Every act of building, learning, or loving is a momentary defiance, a brief sculpting of shape from chaos. And these moments, small as they are, make the universe more interesting, more awake, more filled with stories. Perhaps the truth entropy reveals is that purpose is not something we discover waiting for us in the future. It is something we create in the present, again and again, as long as energy flows through us. And understanding entropy can change the way we see ourselves. Instead of feeling insignificant in the vast flow of disorder, we become participants in the universe's grand transformation. We are not merely drifting along entropy's current, we are shaping tiny islands of structure within it: ideas, art, music, friendships, discoveries. Each one is a bright flare of order against the endless canvas of possibility. Even the act of noticing beauty, a leaf trembling in wind, the color of dusk, the quiet breath of someone sleeping, is a kind of resistance. Awareness itself is a form of low entropy, a pattern carved from the noise. In that sense, consciousness is the universe briefly recognizing its own unfolding. And perhaps that is why entropy feels philosophical at all. It asks us to confront the temporary nature of existence, but it also invites us to marvel at the improbable fact that we are here, thinking, feeling, wondering, within a universe that could have easily been nothing more than a smooth, undifferentiated haze. Entropy gives meaning by contrast. It is the dark night against which the stars shine. But there is one more thread, faint yet shimmering, that entropy leaves trailing behind. If disorder always increases, and if all structures decay, then why do we care so deeply for these fleeting arrangements? Why do we build memories, create art, pursue knowledge, love people, knowing all of it is temporary? Well, perhaps because transience is what makes existence sacred. A beautiful moment would not move us if it had infinite time. A fragile thing would not feel precious if it could not break. Entropy shapes our emotional universe as much as it shapes the physical one. It tells us that nothing is guaranteed, that every configuration of life is a borrowed miracle, that meaning is always carved from impermanence. And with that, another question quietly enters the room. If entropy is the foundation of physics, the sculptor of time, the shaper of life, the guide of technology, the whisperer of meaning, then what remains when all the moments have unfolded? What does it mean to reach the cosmic horizon where entropy is maximized, where no new structures arise, where everything is evenly spread? To reflect on that, to linger on the ultimate stillness entropy predicts, we must step beyond science and into the contemplative space between physics and philosophy, where the universe's destiny becomes a mirror for our own longing to understand existence itself. Well, you see, when we move beyond the philosophical hush of entropy and step into a space that feels almost like an echo chamber of possibility, a new chapter begins to form. One that wasn't written explicitly in the outline, yet one that feels inevitable, because after exploring what entropy is, how it shapes physics, life, time, technology, and meaning, we're left with a lingering question. What else might entropy be whispering to us? What deeper patterns lie just beneath the surface, waiting for us to notice? And that's the thing. Entropy, when followed far enough, becomes not only a scientific principle or a philosophical guide, but a bridge into the unknown, a doorway into emerging ideas that blur the lines between what we know, what we wonder, and what we might someday understand. Perhaps the most intriguing thought is this. Entropy may not simply describe the universe, it may be how the universe thinks. And you know, that sounds strange at first, maybe even a little daring. But consider this for a moment. Information and entropy are tightly linked. Order and probability are inseparable. Meaning is extracted from uncertainty. Everywhere we look, whether at galaxies or neurons, DNA strands or quantum fields, we find systems moving toward configurations of higher entropy while simultaneously producing temporary pockets of order. It is almost as though the universe is performing a kind of cosmic computation, exploring possibilities, selecting pathways, letting complexity bloom before dissolving it again into simplicity. And if we widen our perspective even more, entropy begins to resemble a kind of universal language. When stars fuse elements, when organisms evolve, when civilizations rise and fall, when technologies process data, all of these stories can be told in the vocabulary of entropy. It is a language of transitions, of shifts in probability, of energy flowing from concentrated forms to dispersed ones. In this sense, entropy isn't merely about disorder. It is about movement, transformation, becoming. Maybe that's why entropy feels almost spiritual at times, not in a mystical sense, but in the way it asks us to confront both the fragility and the fullness of existence. Every moment of your life, from the quietest breath to the most profound realization, is supported by entropy's steady, unbroken logic. Your body takes in energy to maintain its improbable structure. Your mind forms thoughts by shaping patterns against randomness. Even your emotions, fleeting as they are, ripple through neural circuits that are deeply entangled with thermodynamic laws. But perhaps the most fascinating frontier, the one we're only beginning to sense, is the possibility that entropy could be tied to consciousness in ways we do not yet understand. You see, every thought you have reduces uncertainty. Every recognition, every memory, every decision is a narrowing of possibilities. Consciousness may operate as a low-entropy phenomenon emerging from the high-entropy sea of neural activity. And yet, consciousness also generates entropy. Electrical currents flow, neurons fire, heat escapes from the brain. This duality, consciousness creating order while requiring disorder, mirrors the duality of life itself. It's as if entropy forms the backdrop on which awareness plays its fragile, shimmering notes. And when you wonder about something, really wonder, you are participating in the universe's own journey from uncertainty toward clarity. And well, perhaps entropy also reveals something about the nature of creativity. When an artist paints, or a writer crafts a story, or a musician improvises a melody, they impose structure on the world. They create a momentary island of low entropy, a pattern that did not exist before. But in doing so, they expend energy, release heat, generate entropy elsewhere. Meaning is never free. Beauty always has a thermodynamic cost, and that cost, strangely, makes the creation feel more alive. Art becomes a dance with entropy rather than a defiance of it. And consider love, relationship, connection. These too are forms of order, patterns of understanding, trust, memory, held together in a universe that naturally moves toward dispersion. To maintain them, you must invest energy, attention, empathy, time. Without that input, the relationship, like any organized system, dissolves into entropy. This might sound melancholic, but it is actually a profound invitation. It means that love is not passive, it is thermodynamic. It is chosen, maintained, nurtured. The effort is not a flaw, it is the essence. Now let us wander into an even stranger thought. What if entropy is not merely a physical law, but an evolutionary force? Consider the possibility that systems which manage entropy well, those that can harness energy, create order locally while releasing entropy globally, are the ones that survive, reproduce, persist. Stars that fuse efficiently shine longer. Life forms that channel energy more effectively thrive. Civilizations that learn to manage energy sustainably endure. Perhaps entropy is the guiding hand of evolution on cosmic, biological, and technological scales. In this way, entropy becomes not just a description of what happens, but a principle that shapes what can happen. It sets the landscape of possibility. It determines which structures can exist and for how long. It tells us that stability is rare, that order is fragile, that change is fundamental. But it also tells us that complexity, meaning, consciousness, all of these phenomena can emerge as temporary but extraordinary exceptions carved from the rising tide of entropy. Some modern thinkers even suggest that the universe might be a kind of entropy optimizing system, always drifting toward states that maximize its capacity for transformation. From this viewpoint, entropy becomes not a destroyer, but a creator, a sculptor of landscapes, both physical and conceptual, a force that invites the universe to explore every avenue of its own potential. And once we look at entropy through this lens, a new sense of humility arrives. We realize that every idea, every achievement, every life is a brief flare of order made possible only because the universe allows it. And in that realization, perhaps we feel a quiet gratitude, not despite entropy, but because of it. Because without entropy's direction, the universe would never change, never evolve, never awaken into the complexity we now witness. And yet, as we stand here in the philosophical twilight of 2025, a gentle question begins to rise from the horizon of thought. If entropy governs the unfolding of everything we know, stars, life, consciousness, meaning, then what lies beyond this unfolding? What becomes of a universe that continues its long journey toward equilibrium? And what becomes of us, small islands of thought, living within this cosmic drift? Well, to explore those questions, to step beyond philosophy and into the vast, almost meditative contemplation of the universe's final chapters, we must follow entropy into its ultimate horizon, where physics, cosmology, and human longing converge into a single quiet inquiry about the fate of all things. Well, you see, as we come gently to the closing arc of this long wandering through entropy's many worlds, it feels a little like stepping out of a vast observatory after a night spent staring into the cosmos. Your eyes adjust, slowly, to the softness of ordinary light, yet something inside you remains expanded, stretched by the things you've glimpsed. And that's the thing. Once you've walked with entropy through physics, through life, through time, through technology, through meaning itself, the world doesn't return to the way it looked before. It shimmers differently. A cup of cooling tea is no longer just a cup of tea. A tidy room is no longer simply tidy. A memory, a breath, a star. They each reveal themselves as brief, exquisite shapes rising and falling within the great current of disorder that sweeps the universe forward. Perhaps the deepest realization is that entropy isn't an enemy, nor a flaw in the universe's design. It is the universe's design. It is the quiet principle by which everything unfolds, the gentle hand that turns potential into history. Without entropy, nothing would happen. No stars igniting, no cells dividing, no rivers flowing, no minds awakening into thought. The universe would be frozen, perfectly still, with no before or after. Entropy is not the force that brings decay. It is the force that brings change. And change is the seedbed of everything we hold dear. You know, we often think of disorder as something to fight against. A messy house, aging objects, fading memories. But if we listen carefully, entropy tells a different story. It reminds us that disorder is not failure, but continuation. A room grows messy because life is being lived inside it. A battery ages because energy has been used to move the world. Food spoils because life's chemistry keeps unfolding even after harvest. Entropy doesn't oppose life. Life happens within it, because of it. And that realization softens something in us. Suddenly, the world's imperfections begin to feel less like problems and more like signatures of motion, signatures of being alive. But perhaps what moves me most is the way entropy draws a thread between the smallest and largest scales of existence. A drifting molecule and a dying star obey the same law. A melting ice cube in the far future of the cosmos follow the same direction of time. A cloud forming above a mountain ridge and the slow expansion of space itself both trace their origins to entropy's quiet influence. When you begin to see this unity, this symmetry between the intimate and the infinite, you start to sense that the universe isn't a collection of disconnected things. It is one continuous process, flowing through patterns we momentarily inhabit, and in that flow, humans take on a strangely beautiful role. We are creatures who notice entropy. We feel it as time. We witness it as aging. We fight it through art, science, memory, love. Every story we tell, every structure we build, every moment we cherish is a small act of shaping order in a world that leans towards spreading out. It is not futile. It is magnificent precisely because it is temporary. Think for a moment about a photograph. A single captured instant. A child smiling. A landscape glowing under the last light of day. The photograph holds a pattern that existed only for a moment before entropy carried it into the past. And yet, in holding it, we create meaning. We resist forgetting. We carve a fragile but luminous structure against the soft erosion of time. Entropy makes memory necessary. It makes love urgent. It gives weight to choices and depth to presence. Without entropy, every moment would be interchangeable, nothing more special than anything else. But because entropy carries things away, we reach toward them with reverence. We pay attention. We care. And perhaps that is what entropy ultimately teaches, that value is born from impermanence. Beauty is heightened by fragility. Meaning grows from the awareness that nothing stays the same. To live is to participate in a universe that is constantly becoming something new, even as it lets go of what came before. In the scientific chapters, we followed entropy through equations, engines, stars, black holes. We discovered its presence in data, in biology, in weather and memory. But beneath all these details lies a gentle, almost poetic truth. Entropy is the story of the universe, learning how to expand, how to transform, how to explore the vastness of its own possibilities. And if entropy is the universe's storyteller, then we, tiny sparks of consciousness, are the listeners and the interpreters. We give language to the unfolding. We turn probability into narrative. We transform thermal gradients into architecture, food into thoughts, starlight into wonder. You see, even now, as we sit together in the quiet wake of this long exploration, entropy is at work. Neurons firing, air molecules dispersing, heat tracing soft currents around your skin. And yet, in this fleeting pocket of low entropy, a pattern forms: understanding, curiosity, a sense of connection to something vast. This, perhaps, is the great paradox of entropy. It drives everything toward disorder, yet it allows pockets of extraordinary order to exist long enough for minds to awaken, to question, to learn. Entropy ushers us forward, but we decide how to shape our brief time within its flow. As we look toward the horizon of the universe's future, the cooling stars, the expanding void, the distant equilibrium, it might be tempting to feel small. But entropy tells a different story. It says that being temporary does not diminish meaning, it enhances it. A finite life, a finite civilization, a finite cosmos, all of these are stages where remarkable patterns appear for a while, shine brilliantly, and then dissolve back into the wider sea of possibility. And so, the lesson entropy leaves us with is not despair, but humility. Not resignation, but awe. Because the very fact that we can contemplate entropy, that we can understand even a small part of the universe's unfolding, means that we too are part of the universe waking up. But well, if this is where entropy brings us in 2025, into wonder, into reflection, then perhaps there is still one more step to take, one more thread to follow. Because even as entropy explains so much about change, time, and existence, there is a deeper question lingering just beyond the edge of thought. If everything drifts toward disorder, then why does the universe begin ordered at all? Why was there a moment, a first moment, when entropy was low enough for stars, life, and consciousness to emerge? To explore that mystery, to trace entropy back to the dawn of creation and forward into the fate of everything, we must step into a chapter where cosmology, quantum physics, and philosophy intertwine more tightly than ever before.